Across a chasm of 320 million light-years, where the fabric of spacetime stretches thin and cool between the islands of organized matter, there lies a concentration of mass so profound it warps the very geometry of the cosmos around it. This is the Coma Cluster, a celestial kingdom composed of more than 1,000 galaxies, all bound together by a shared, inescapable gravitational embrace. To the telescopic eye, it appears not as a dazzling collection of spiral arms and vibrant nebulae, but as a swarm of faint, ovoid smudges, each a galaxy unto itself, glowing with the soft, tired light of ancient suns. The entire superstructure is immersed in a far fainter, almost imperceptible haze, an ethereal medium of superheated gas detectable only in the X-ray spectrum, and a ghostly intracluster light composed of countless orphan stars, flung from their parent galaxies over billions of years of chaotic interaction. This vast assemblage, spanning millions of light-years from edge to edge and containing the mass of quadrillions of suns, is not a cradle of cosmic creation. It is a necropolis. It is one of the universe's great galactic graveyards, a place where the processes of stellar birth have largely ceased, leaving behind silent, monolithic structures composed almost entirely of aged and dying stars. The dominant color is not the brilliant blue of youthful, massive suns, but the somber, ruddy yellow of a population in its final, extended senescence. These galaxies are overwhelmingly elliptical and lenticular, smooth and featureless, their dynamic, star-forming histories long since erased. They drift through the cluster's core not with the vibrant energy of creation, but with the stately, inexorable momentum of cosmic relics. The sheer scale of this quiescence, this coordinated cessation of activity across 1,000 galactic systems, presents a profound cosmological question, written not in words but in the languid orbits of its silent members. What immense and patient force could orchestrate such a widespread and terminal decline, transforming a region of vibrant galactic evolution into a silent, sprawling mausoleum of cosmic history? The process that transforms a vibrant, star-forming galaxy into a quiescent relic within a cluster is not a single, catastrophic event, but a slow, grinding series of environmental trials. It is a death by 1,000 cuts, administered over hundreds of millions of years as a galaxy falls from the relative emptiness of the intergalactic void into the dense, hostile heart of the cluster. The primary agent of this transformation is a phenomenon known as ram pressure stripping. As the galaxy plunges towards the cluster's gravitational center at speeds exceeding 1,000 km per second, it encounters the intracluster medium, the tenuous but incredibly hot plasma of gas that fills the space between the galaxies. This medium, with a temperature of millions of degrees Kelvin, acts like a cosmic wind. For the galaxy, which carries its own vast reservoir of cold, neutral hydrogen gas, the essential fuel for forming new stars, this encounter is devastating. The relentless pressure of the hot wind scours the galaxy, stripping away its cold gas clouds and long, trailing filaments that stretch for tens of thousands of light-years behind it. Deprived of its raw material for creation, the galaxy's star-forming nebulae flicker and die out. The brilliant blue and pink hues of HII regions, the stellar nurseries where massive stars are born, vanish from its spiral arms, leaving only the enduring light of its pre-existing, aging stellar population. The galaxy is effectively strangled, its creative potential bled away into the surrounding intergalactic space. Concurrent with this slow starvation is a process of gravitational torment. The immense, collective gravity of the cluster, dominated by an unseen halo of dark matter, exerts a powerful tidal force on the infalling galaxy. This cosmic tide stretches and distorts the galaxy's structure, warping its delicate spiral arms and pulling at its outermost stars. Over eons, these repeated gravitational insults work to puff up the galaxy, transforming its flat, rotating disk into a more randomized, spheroidal distribution of stars. The combination of gas stripping and gravitational harassment is a brutally effective mechanism for galactic mortality, systematically dismantling the machinery of star formation and reshaping the galaxy's very form until it settles into the featureless, reddish glow of an S0 or elliptical galaxy, a permanent and passive resident of the cosmic graveyard. Within this silent congregation of fated giants, one can select a single specimen for closer inspection, a representative example of a system that has completed its long journey into senescence. It is an elliptical galaxy, designated by astronomers with a simple catalog number, but representing a repository of 10 billion years of cosmic history. It appears as a vast, diffuse ball of light, brightest at its core and fading gently into the surrounding darkness. There are no sharp edges, no spiral arms tracing pathways of ongoing creation, no dark lanes of interstellar dust to obscure the view. Its structure is one of serene, triaxial symmetry, a testament to a system that has achieved a state of profound gravitational equilibrium. Its light, when broken down into a spectrum, tells a story of absence. The characteristic emission lines from ionized hydrogen, the telltale sign of active star formation, are gone. The dominant signal is the continuous spectrum of countless stellar photospheres, a composite light that peaks in the yellow and red wavelengths. This is the integrated glow of hundreds of billions of stars, the vast majority of which are ancient, low-mass objects. They are K-type and M-type main sequence stars, or red dwarfs, which sip their hydrogen fuel so slowly that their lifespans can exceed the current age of the universe. Interspersed among them are the more luminous red giants, stars similar to our own Sun that have exhausted the hydrogen in their cores and have swollen to enormous size, their outer layers glowing with a final, brilliant burst of activity before their inevitable collapse. The brilliant, massive, and short-lived O and B-type stars that dominate the light of a young spiral galaxy are entirely absent here. They burned through their fuel and exploded as supernovae billions of years ago, and with the galaxy's gas supply long since stripped away, no new generations have risen to take their place. The galaxy is a closed system, a stellar retirement community on a cosmic scale. Its stars are locked into long, slow, elliptical orbits that cross and weave through the galactic center, a randomized swarm of motion that stands in stark contrast to the orderly, coplanar rotation of a spiral disk. This galaxy is a ghost of its former self, its form and color a direct consequence of its violent past and its sterile present. It is a monument built from the accumulated light of survivors, a silent, glowing testament to the cessation of cosmic creativity in one of the universe's most densely populated regions. Beneath the placid, golden glow of the elliptical galaxy's aging stars lies a second, far more cryptic population, an immense and unseen graveyard of stellar corpses. This is the galaxy's true necropolis, a vast collection of degenerate remnants that no longer produce light through nuclear fusion. The most numerous of these dark residents are the white dwarfs. For every star like our Sun that has ended its life, a white dwarf is born. These objects are the incredibly dense, hot cores left behind after a star has shed its outer layers to form a planetary nebula. A typical white dwarf packs the mass of the Sun into a volume no larger than the Earth, resulting in a density so extreme that a single teaspoon of its matter would weigh several tons. This matter is not ordinary, it is electron degenerate, a state where quantum mechanical pressure prevents further gravitational collapse. These stellar embers are born with surface temperatures exceeding 100,000 Kelvin, glowing with a brilliant white light, but they possess no internal energy source. They are cosmic cinders, destined to spend trillions of years radiating their residual heat into the void, slowly cooling and fading in luminosity until they become cold, inert black dwarfs, invisible crystallizations of carbon and oxygen. Far more extreme are the neutron stars, the remnants of stars born with between 8 and 20 times the mass of our Sun. Their deaths are not gentle dissolutions but cataclysmic supernova explosions, events that briefly outshine the entire galaxy. What remains is a core so compressed by gravity that protons and electrons are forced together to form a pure ball of neutrons. A neutron star contains more mass than the Sun within a sphere just 20 kilometers in diameter. Its density is incomprehensible, a single cubic centimeter outweighing Mount Everest. Many are born spinning hundreds of times per second, their immense magnetic fields sweeping beams of radiation through space like cosmic lighthouses, appearing to observers as pulsars. These objects are clocks of astonishing precision, but they too are cooling, their rotation slowly winding down over millions of years. Finally, there are the stellar mass black holes, the final state for the most massive stars of all. Here, gravity has overwhelmed all other forces, crushing the stellar core to an infinitesimal point of infinite density, a singularity. Surrounding this point is the event horizon, a spherical boundary from which not even light can escape. These objects are the ultimate stellar ghosts. They are detected not by any light they emit, but by their gravitational influence on their surroundings, by the wobble of a companion star caught in their orbit, or by the intense X-rays produced as they siphon matter from a nearby object. Within this single, quiescent elliptical galaxy, there are billions of these dark remnants, a hidden mass that silently shapes the galaxy's gravitational potential, a testament to the full spectrum of stellar evolution, from the quiet fading of sun-like stars to the violent collapse of cosmic behemoths. To comprehend the existence of these immense galactic graveyards, one must zoom out again, far beyond the confines of a single galaxy cluster, to the largest scale structure in the known universe, the cosmic web. This is the fundamental architecture of the cosmos, a vast, interconnected network of filaments and voids that emerged from the tiny quantum fluctuations present in the primordial universe. The cosmic web is not made of ordinary matter, but is predominantly a scaffold of dark matter, the mysterious, invisible substance that constitutes over 80% of the matter in the universe. We cannot see it, but we can map its presence through its gravitational influence on the light from distant galaxies, a phenomenon known as gravitational lensing. Cosmological simulations, which model the evolution of the universe under the influence of gravity and dark energy, consistently show that dark matter collapses over billions of years into a complex, web-like pattern. It forms immense, dense halos connected by long, tenuous filaments, which in turn surround vast, empty regions known as cosmic voids. The ordinary matter we can see, the gas, dust, and stars, is a secondary component, drawn by gravity to trace this underlying dark matter structure. Galaxies form and evolve along the filaments, like beads on a string, slowly migrating along these cosmic highways towards the points where the filaments intersect. These intersections are the most massive, densest nodes of the cosmic web. They are the regions of the deepest gravitational potential wells, and it is here that galaxy clusters are born. A galactic graveyard like the Coma cluster is not a random collection of galaxies, it is the fully mature, gravitationally dominant nexus of multiple cosmic filaments. It represents the culmination of 13 billion years of gravitational assembly. The galaxies within it are those that have completed their long journey down the filaments and have fallen into the cluster's profound gravitational well, where the environmental processes of stripping and harassment begin. Therefore, the graveyards are not anomalies, they are an inevitable consequence of the hierarchical model of structure formation. They are the most gravitationally evolved, most massive, and most densely populated environments the universe has to offer. They are the cosmic cities, built at the junctions of the great intergalactic thoroughfares, and like any metropolis, they are places of intense interaction, transformation, and ultimately, a form of cosmic urban decay where the raw materials for new growth have been exhausted and consumed. These repositories of cosmic finality are far more than static monuments to extinct processes, they are invaluable archives and laboratories, offering profound insights into the history and fundamental laws of the universe. The vast population of white dwarfs within a dead galaxy functions as a collective cosmic clock. Because the physics of their cooling is relatively well understood, the luminosity and temperature of the faintest, oldest white dwarfs in a cluster can be used to place a lower limit on the age of the universe itself, providing an independent check on measurements derived from the cosmic microwave background. This technique, known as white dwarf cosmochronology, effectively reads the time from the cooling embers of long-dead stars. Furthermore, the distribution of white dwarf masses provides a fossil record of the star formation history of the galaxy. It tells astronomers about the initial mass function, the original distribution of stellar masses, of stars born billions of years ago, a crucial piece of information that is otherwise lost to time. The neutron stars and pulsars scattered throughout these graveyards serve as probes of extreme physics. The matter inside a neutron star is the densest observable material in the universe, a state of cold, ultradense nuclear matter that cannot be created in any terrestrial laboratory. By studying the subtle variations in their spin and the properties of their radiation, physicists can constrain the equation of state for nuclear matter, testing the limits of the strong nuclear force. When two neutron stars in a binary system spiral together and merge, they produce a kilonova explosion and a burst of gravitational waves. These events, now detectable by observatories like LIGO and Virgo, are confirmed to be the primary sites of the rapid neutron capture process, or R process, the cosmic forges that create more than half of all the elements heavier than iron, including gold, platinum, and uranium. The black holes, both stellar mass and supermassive, provide the most stringent tests for Einstein's theory of general relativity. The precise timing of pulsar signals from a binary system containing a pulsar and a black hole can reveal the subtle warping of spacetime and the emission of gravitational radiation, confirming the theory's predictions with astonishing accuracy. Therefore, the galactic graveyard is not a place of informational death. It is a library of cosmic history, a high-energy physics laboratory, and a proving ground for our understanding of gravity, all preserved within the silent orbits of its deceased and dying inhabitants. Deep within the ancient star fields of these galactic graveyards, particularly within the dense, spherical swarms of stars known as globular clusters that orbit the main galaxy, lies one of the most compelling and persistent mysteries in modern astrophysics, the search for intermediate mass black holes. The universe presents astronomers with a stark dichotomy in the black hole population. On one end of the scale are the stellar mass black holes, with masses ranging from a few to perhaps 100 times that of our Sun, the well-understood remnants of massive star collapse. On the other end are the supermassive black holes, the behemoths weighing millions to billions of solar masses that reside at the centers of nearly all large galaxies. Between these two extremes lies a vast and puzzling desert, a mass gap, from roughly 100 to 100,000 solar masses where black holes are inexplicably rare. The existence of these intermediate mass black holes, or IMBHs, is a crucial missing link in our models of cosmic structure formation. They are the theoretical seeds from which supermassive black holes may have grown in the early universe. One leading hypothesis for their formation points directly to the dense environments found in galactic graveyards. In the heart of a young, massive globular cluster, thousands of stars are packed into a space only a few light-years across. In this chaotic environment, the most massive stars would quickly sink to the center due to a process called dynamical friction. Here, they could undergo a runaway series of collisions and mergers, creating a single, extraordinarily massive star that would then collapse to form an IMBH. Alternatively, an IMBH could grow over time by cannibalizing other stars and stellar mass black holes that wander too close to the cluster's core. Finding them, however, is exceptionally difficult. An IMBH in the center of a globular cluster would be quiescent, not actively feeding on enough material to produce the bright accretion disk that makes supermassive black holes visible. Astronomers must therefore hunt for their subtle gravitational signatures. They meticulously track the motions of individual stars near the cluster's center, looking for evidence of stars moving at anomalously high velocities, a telltale sign that they are orbiting a massive, unseen central object. Another potential signature is a tidal disruption event, a rare but spectacular flare of radiation produced when an unlucky star passes too close to the IMBH and is torn apart by its immense tidal forces. While a handful of tantalizing candidates have been identified through these methods, conclusive proof remains elusive. The confirmation of a healthy population of IMBHs within these ancient stellar systems would not only solve the mystery of the mass gap but would also provide a clear pathway for the growth of the supermassive giants, connecting the death of the first massive stars to the colossal engines that now govern the centers of galaxies. At the gravitational heart of every massive elliptical galaxy, anchoring the entire system of aging stars and stellar remnants, lies the largest and most enigmatic resident of the graveyard, a supermassive black hole. These objects are not mere curiosities, they are fundamental components of galaxy evolution. In a young, gas-rich galaxy, this central black hole can be a ferociously active engine. As gas and stars fall towards it, they form a swirling, superheated accretion disk, a vortex of matter that shines with a brilliance capable of outshining the combined light of all the galaxy's stars. This phenomenon creates an active galactic nucleus, or AGN, the most luminous of which are known as quasars. In the context of a galactic graveyard, however, the central engine is typically dormant. The supply of cold gas that once fed it has been exhausted or expelled, and the black hole now sits in quiet starvation, its presence betrayed only by the rapid, frantic orbits of the stars closest to the galactic core. Yet, the influence of this sleeping giant is profound and permanent, etched into the very structure of the galaxy it inhabits. Astronomers have discovered a remarkably tight correlation, known as the M-sigma relation, linking the mass of the supermassive black hole to the velocity dispersion, a measure of the random motions, of the stars in the galaxy's central bulge. This relationship holds across a vast range of galaxy types and sizes, and it implies a deep, symbiotic connection, a process of coevolution where the galaxy and its central black hole grow in lockstep. The black hole is not a passive occupant, it is an active regulator of its host's growth. The immense energy output from its active, quasar phase, in the form of powerful jets of relativistic particles and intense radiation, is believed to be a primary mechanism of what is called AGN feedback. This feedback can heat the gas throughout the galaxy, preventing it from cooling and collapsing to form new stars. In its most violent phases, it can drive galactic-scale winds that expel the gas from the galaxy entirely. In this sense, the supermassive black hole acts as a thermostat, or even a self-destructive agent, for its own host. By shutting down star formation from the inside out, it plays a crucial role in transforming a vibrant spiral into a red and dead elliptical. The central black hole helps to create the very graveyard in which it now resides, a quiescent monarch presiding over a kingdom it helped to sterilize. Its mass is a permanent record of its past activity, a silent measure of the energy it once unleashed to shape the destiny of its billion-star host. The galactic graveyards of the present-day universe, such as the Coma cluster, are not the final state of cosmic evolution, they are merely a preview, a glimpse into the ultimate fate of all matter and structure in the cosmos. Projecting the known laws of physics forward over timescales that dwarf the current age of the universe reveals a future of profound emptiness and decay. The current era, the stelliferous era, in which the universe is lit by the fusion-powered glow of stars, is but a fleeting moment. In approximately 100 trillion years, the process of star formation will have ceased everywhere, not just in clusters. The smallest, longest-lived red dwarf stars will have finally exhausted their hydrogen fuel, and the last of these stellar fires will flicker out. The universe will then enter the degenerate era, a period of unimaginable duration and darkness. The cosmos will be populated only by the remnants of stars, brown dwarfs, cooling white dwarfs, neutron stars, and black holes, all orbiting the skeletal remains of their parent galaxies. The galaxies themselves will begin to dissolve. Over timescales of 10 to the power of 19 to 10 to the power of 20 years, a process called dynamical relaxation will slowly alter the orbits of these stellar corpses. Close gravitational encounters will gradually eject the majority of them from their host galaxies, flinging them into the lonely, expanding void of intergalactic space. A small fraction will lose energy and spiral inward, to be consumed by the central supermassive black hole, which will slowly grow in mass as it swallows the last vestiges of its galaxy. Eventually, even the galaxies themselves will merge, as the clusters and superclusters of today slowly coalesce into single, hypermassive dark agglomerations. But even these structures are not eternal. On timescales so vast they defy human comprehension, from 10 to the power of 37 years onward, the universe enters the black hole era. If theories of grand unification are correct, protons themselves are unstable and will eventually decay, causing the degenerate remnants of stars, the white dwarfs and neutron stars, to slowly evaporate into a bath of low-energy particles. Only the black holes will remain, silent gravitational tombs holding the last organized mass in the universe. Yet, even they are not immortal. According to the principles of quantum mechanics, black holes must radiate energy, a phenomenon known as Hawking radiation. Over googolls of years, 10 to the power of 100, and far, far longer for the most massive ones, even the supermassive black holes will slowly evaporate, converting their mass back into a faint whisper of thermal radiation. The universe will then enter its final, hypothetical state, the dark era. A cold, near-empty void, filled only with a diffuse, ever-cooling gas of photons, neutrinos, and other elementary particles, where the temperature approaches absolute zero and all structure and all history have been erased. The ultimate graveyard is the universe itself. Returning from the unfathomable abyss of the far future to the present moment, the Coma cluster reappears in the mind's eye, its faint, ancient light traversing the void. It is no longer merely a collection of silent galaxies, but a rich, multi-layered text revealing the past, present, and future of cosmic structure. These galactic graveyards are the physical embodiment of gravity's relentless, patient work over the full sweep of cosmic time. They are archives, their stellar populations holding a fossil record of star formation from an era when the universe was young and prolific. The chemical composition of their stars and intracluster gas tells the story of generations of supernovae, the alchemical engines that forged the elements necessary for planets and for life. They are also unparalleled laboratories. The extreme density of neutron stars allows us to probe the behavior of matter under conditions far beyond our reach on Earth, while the elegant dance of binary pulsars and black holes provides the most precise confirmations of Einstein's general relativity, a theory that underpins our entire cosmological model. The mysterious absence of intermediate mass black holes and the ongoing search for them within ancient globular clusters represent a frontier of our knowledge, a missing chapter in the story of how the universe builds its largest structures. Most profoundly, these graveyards serve as signposts, pointing the way toward the universe's ultimate destiny. They are microcosms of the degenerate era, living previews of a future where all stars will have burned out, leaving behind only cooling embers and gravitational ghosts. Yet, even in this state of apparent death, the system is not static. A subtle dynamism persists. White dwarfs continue their slow, inexorable cooling. Neutron stars gradually spin down, their magnetic fields decaying over eons. The supermassive black holes at the centers of these galaxies, though dormant, remain gravitational anchors, their presence a constant influence on the surrounding stars. The entire cluster is still in the process of settling, its constituent galaxies still orbiting and interacting, their slow dance governed by the unseen hand of dark matter. The graveyard is not an end point, but a phase in an evolutionary process of incomprehensible length. It reminds us that our human perspective, our sense of activity and quiescence, is calibrated to a fleeting timescale. On the grand stage of the cosmos, the galactic graveyard is not a place of stillness, but a place of transformation, a testament to the enduring power of physical law and the ceaseless, patient evolution of the universe itself.